Module 3.2. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 3.2. How do researchers design studies? Why do some variables exist an association when no causation is present? Definition. When confounding is present, we cannot determine if the change in the response variable is due to the explanatory variable or to a third variable. One way that confounding may occur is when a third variable that is not accounted for in the study and associated with both the explanatory variable and the response variable is present. These variables are called confounding variables. Alternatively, confounding occurs when a study is flawed and the effects of multiple explanatory variables cannot be separated from one another. Confounding may explain why we see a pattern between the explanatory and response variable even when there is no causation present. Whenever confounding is present, or may be present, we cannot conclude that there is a causal link between the variables. One way to think of the relationship between the types of variables is to think of a system of gears, where each gear represents one of the variables we have discussed. Suppose that we have a gear representing the explanatory variable and a gear representing the response variable. We want to see if when the explanatory variable is turned, it is responsible for the response variable turning. Notice when the middle gear is turned, the explanatory variable and response variable will also turn, even though the explanatory variable does not ever touch the response variable. We would say that we have no association since both gears turn, but no causation since the gears do not touch. The third gear in the middle is the confounding variable. Notice that the confounding variable touches both the explanatory and the response. This is just one possible scenario. We could have more complex scenarios where both the explanatory and confounding variable touch the response variable gear. In either case, the explanatory gear is not solely responsible for the response gear turning. When the explanatory variable is causing a change in the response variable, there is no confounding variable present. Notice in the picture that the explanatory gear touches the response variable gear. Recall the shark attack example. The increase in ice cream sales does not cause an increase in shark attacks. Warmer temperatures cause increased ice cream sales and the increase in shark attacks. So here, the confounding variable was weather. Another way for confounding to occur is when a study is flawed and the effects of multiple explanatory variables cannot be separated from one another. For example, suppose that you took a class where you performed poorly on the first exam. To prepare for the next exam, you visit the tutoring center, visit office hours for help, and work all the problems in the textbook. On the second exam, you score 100. You want to know if visiting the tutoring center caused your exam grade to increase. In this case, you do not know which of the three helped your second exam score. You cannot conclude that visiting the tutoring center caused your exam score to be higher. Your turn. Read the following relationships and identify a possible confounding variable. Pause the video, and when you return, we'll look at some potential answers together. The total amount of salmon consumed and the total amount of asparagus consumed worldwide are closely related over the past 100 years. The confounding variable here is world population size. Over the last 100 years, the number of people has increased, and therefore the amount of salmon eaten has increased. Similarly, the amount of asparagus eaten has increased. People who own a private movie theater are more likely to buy a sports car. The confounding variable is wealth. Wealthy people are more likely to buy a sports car. Similarly, they are more likely to own a private movie theater. People with shorter hair tend to be taller. The confounding variable is gender. Males tend to be taller and have short hair. Females tend to be shorter and have long hair. Notice here, we're not saying that this always holds true for the explanatory and response. We're just talking about overall trends. If plots cannot tell us about causation, how do researchers determine if there is a causal relationship? Whether or not causation can be established between two variables depends on how the data for a study was collected. Some studies are backward-looking, retrospective, or forward-looking, prospective. When a researcher collects data by simply observing and does not influence the variable in any way, we call the study an observational study. Observational studies can be descriptive or comparative. We will look at 3 different types of observational studies. Cohort study. Groups with particular characteristics are known as cohorts. A prospective study involving the comparison of cohorts is called a cohort study. Retrospective cohort studies can also be performed when trying to compare the risk of developing a disease to some already identified exposure factor. Follow this link, which is also located in the script, to read more about cohort studies. Case control study. A case control study is a retrospective study where subjects with the outcome of interest, case subjects, are compared to subjects without the outcome of interest, control subjects. Existing data for both the case subjects and control subjects are obtained to determine what factors related to a subject becoming a case or a control. Read more at this link here, which is also located in the script. Cross-sectional study. In a cross-sectional study, the data are collected at a particular time point and represent a cross-section of time. The outcome and variables of interest are measured at the same time. When a researcher collects data by actively controlling the explanatory variables, we call the study an experiment. To establish causation, the researcher must collect the data through an experiment. The reason is that experiments can help prevent confounding. This brings us to an important fact. Observational studies can almost never be used to establish causation. The invalid assumption that correlation implies causation is probably among the 2 or 3 most serious and common errors of human reasoning. As a public health professional, you should pay close attention to this important fact. There are times you will be presented with information which claims that 2 variables have a causal relationship, but the data will have been collected from an observational study. You want to be able to identify these claims and critique them. Your turn. Read the following studies and determine if they describe an observational study or an experiment. Pause the video here, and when we come back, we'll look at them together. A statistics student stood outside the UK library and watched students entering and leaving. She recorded whether the students entered as a group or individuals and kept track of the amount of time spent in the library. She is interested in learning whether or not the students who go to the library as a group spend more time in the library than those who go alone. This is an observational study because the student is only observing what people are doing without influencing whether they go to the library alone or in a group. A veterinarian would like to see if grain-free dog food is better for dogs he examines than food with grain. He supplies 5 dog owners with grain-free food for 1 month and a different 5 dog owners dog food with grain. After the month is over, the dogs come into the clinic and he measures different health markers. This is an experiment because the veterinarian is telling the dog owners what type of food to feed the dog for the month during the study. How can experiments help us avoid confounding? Performing an experiment does not guarantee that confounding is not present. Careful setup and execution of an experiment can prevent the chances of confounding being present. The best way to prevent confounding is to assign values of the explanatory variable randomly. Definition: in a randomized experiment, the explanatory variable for each subject is assigned randomly before the response variable is measured. The different levels of a single explanatory variable are known as treatments. To set up a randomized experiment, we can randomly divide the subjects into groups and assign a different treatment to each group. Because the subjects are randomly assigned to the treatments, the explanatory variable is not associated with any other variables. Confounding is eliminated. Suppose that we have the following people volunteer for a study. In the study, we would like to compare aspirin to Tylenol to see which drug alleviates a headache more quickly. Notice that the two treatments are aspirin and Tylenol. Our first step is to assign each person to one of two groups randomly. We can do this by assigning each person a number 1 to 12 and using a random number generator to select 6 numbers to place in group 1. Suppose a random number generator tells me that subjects 1, 4, 5, 6, 9, and 10 should be in group 1, resulting in the following groups. Group 1 would consist of these subjects, and group 2 would consist of these. All the subjects in group 1 will receive Tylenol, and the subjects in group 2 will receive aspirin. If a randomized experiment yields a significant difference between the two groups with respect to the response variables being studied, we can establish causation from the explanatory to the response variable. For more information, read this article. This concludes the Module 3.2 video.